It's my pleasure to introduce Selwyn, coming to us all the way from Singapore, who's going to tell us about the planar graph coloring. Selwyn.
Thank you, Peter. Yeah. So, hi friends. I'm very honored to be allowed to speak here at this conference. It's kind of a shame that I couldn't come in person, but hopefully the situation will become better soon, and then we can have more on-site participation. So what I'm going to be talking about today is, so I'm going to be talking about the coloring of graphs. We've had just slightly over half the talks in the conference, and it's been a very good series of talks so far. Yesterday, I think Linda spoke about coloring of graphs, but at the level of Borel. So what I'm going to do today is I'm going to be going at the level of Witt-Koenig's lemma. And I also realized that I am the only thing standing between the on-site participants and the excursion. So I will try not to give too bad a talk. And finish on time. So now the story is the recursive graphs have actually been studied for quite a while back, but somehow I don't think they've kind of really gathered the attention that they deserve. And some of the work, early work of Bean and Schmerl, and this was actually proven around the time or even slightly before the time that the four-color theorem was proved. So it's actually quite interesting, this fact. All the work that I will be talking about in this talk is joined with Cole, who is a student at NTU. Okay, so the story starts from the following well-known theorem, the four-color theorem by Appel and Harkin in 1976, where they showed that every simple planar graph on the plane can be colored with at most four colors. And so what we're going to be doing is we're going to be examining the effectiveness of this theorem. So I was quite surprised when I was looking around for stuff relating to coloring of graphs that actually this thing actually, as far as I know, and I asked quite a few people that this hasn't actually been studied before. So yeah, so that's interesting thing. So I think perhaps many of us have seen this this picture on floating around on the internet. So here you can see a four coloring of the map of the states of the US. And so the map coloring problem is a very well-known problem that goes back to the previous century. And the problem here is to color each region of a map so that two contiguous regions do not have the same color. And actually, this can actually be turned into the language of graph theory. So in this particular four coloring of the map of the states of the US, actually, if you notice, the state of Nevada, which is let me see, I think it's this state that's colored green over here. If my geography is sound, and if you notice, this particular region here actually has 5 neighbors. So if you were to color this map, in particular Nevada green, then you will have to go, like you could go blue, red, and then the last neighbor here, which is the 5th one, will have to avoid the 3 colors around him. So this map cannot be colored in 3 colors. But anyway, 4 colors is sufficient in this case. And the story goes that the problem was, as far as is known, can be traced back to Guthrie, who proposed this conjecture in the 1800s while trying to color the map of England. So no one really knows why he was trying to do that, but that he was. And so he gave it to his brother, who then asked his professor, who was De Morgan at the time, very famous and well-known, who kind of popularized the conjecture at the time. And it took a while for the first incorrect proof to come up. if the proofs were correct. And the proof stood unchallenged for 11 years. And in sometime later, he would then found the flaw in the argument in the first proof, who then exploited that to actually get a proof of the 5-color theorem. Now the 5-color theorem is much easier to prove than the 4-color theorem, and perhaps we'll say something about that later on. But anyway, this theorem was finally proved, perhaps about 100 years later. And it turns out that it took such a long time to prove, not because the main part of it was hard, but because it actually came down to needing certain kinds of algorithmic methods. And basically, what at least in these proofs, what was used was that they reduced the proof to a small number of minimal counterexamples, and then you just have to check one by one that these cases were not possible. And this was simplified and reproved by Robertson, Sanders, Seymour, and Thomas, and which is perhaps the proof that most of us are familiar with. Okay, so maybe I'll just start off just quickly, just showing you the 5-color theorem. This is much easier to prove than the 4-color theorem, and it goes the following way. So as with almost all proofs in graph theory, this is by induction. And so by the Euler characteristic, which is the theorem about vertices, faces, and edges that all of us know about planar graphs, one can deduce that there must be a vertex with degree at most 5. And what you do is you take such a degree and then you remove it from the graph, and then by induction you can color the remaining vertices, which are depicted in white, with 5 colors, as well as the rest of the graph, of course. And then now what you do is you add it back, and you say, okay, so I can color the 5 neighbors of vertex V with 5 colors, but how do I color V using only 5 colors? So what you do is you look at the vertex which is colored 1, and you look at what is called a 1-3 campaign chain, which is a sequence which is a chain of connecting vertices which are colored with alternating colors 1, 3, 1, 3, and 1, 3. And you say if there is no chain that starts with 1 and alternates with colors 1 and 3, and which connects to 3 over here, then it's very easy, right? You just reverse the colors 1 and 3 along the chain, and because it doesn't touch this vertex 3, that would swap 1 with 3, and the color 3 here remains, and that frees up color 1 for V. Now, of course, the bad case is if you can find such a chain that starts with 1 and ends with 3. In this case, if you reverse the colors of 1 and 3, that doesn't do anything for you, because 1 and 3 will just be reversed here. But then what you do is you can say, but then because you fix a plane drawing of this graph, then you start in 4 and consider the 4-2 chain that cannot actually go and connect to the 2 here. So then what you do is now you reverse 4 and 2, which will free up the color 4 from the neighbors of V, which you can then use to color V. So it's a very similar argument that was originally used in the failed proof of the 4-color theorem. Right. So what we're going to do is we're going to study the effective content of this statement. So just some rules. All graphs we're going to consider are going to be simple graphs. So what it means is that there are no loops and no multi-edges. But in general, we're not going to limit ourselves to only connected graphs. So a graph in general might have infinitely many components, for example. And the K coloring for a natural number K is just the usual. You want to have a function that assigns to one of the K many colors to the set of vertices, such that vertices which are neighbors are not given the same color. And of course, we're going to consider infinite graphs because well, that's what we do. But by the usual compactness theorem, and there is also a proof using Tikhonov's theorem. Some kind of compactness argument. It's easy to show. The following theorem, which was actually proved by Erdős and de Bruijn, that the infinite graph is k-colorable if and only if every finite subgraph is k-colorable. So we're going to call this later principle locally k-colorable. This was first investigated by Jeff Hurst in his thesis in the context of reverse math. So so first of all, he showed that the previous statement here is equivalent to WKL0, namely that WKL0 is equivalent to the statement that every locally k-colorable graph is k-colorable. And this was improved by Kasach and Hurst that to the statement that every locally k-colorable graph is 2k minus 1 colorable. So of course, if you only have a 2k minus 1 coloring of a k-colorable graph, that makes it a bit harder to reverse to WKL. And they basically in that work they asked if you could detach the dependence of the of k from this parameter here. So namely, what about the statement that every locally k-colorable graph is m-colorable for where k and m are not dependent on each other? And this was shown by Schmo using a pretty elaborate coding that this is also equivalent to the Weak-Koenig's lemma. Okay, so that's what we know so far about local k-coloring. Now, I also want to bring about so before talking about the stuff that we were doing, I just want to give a little bit of mention a little bit of related work on coloring. So I'm going to mostly be looking at vertex coloring, although there are some interesting results and questions about edge coloring as well. An early work by Bean showed that every k-colorable computable graph has a low k coloring, and every time we have the word computable and a low here, that of course reminds us of the low basis theorem, and this in fact is that's how he proved it. The thing is, you have to think about how you can represent vertices and the edges of the tree is going to encode the possible coloring of that node. And because we are looking only at k coloring, that gives us a uniformly bounded tree, the width. Now, so that doesn't tell us whether or not every computable graph has a computable coloring. So what it then showed was that at least for k equals 2, that statement was not computably true. So you can have a computable 2 colorable graph. What I meant was that the statement was computably true for k equals 2. Now, why this is true is because every 2 colorable graph has a unique 2 coloring. So up to permutation of the color, of course. So this is not actually hard to see. But what he also showed was that the theorem was not computably true for k larger than 2. So there is a computable 3 colorable graph, which was also planar. So he could also make the graph planar. And it has the property that not only is it not computably 3 colorable, but it's not actually computably colorable in any number of colors. So in other words, what this actually translates to in reverse math is that the 4-color theorem is not computably true. So that's what kind of generated interest, at least for me, for looking at this theorem. So we'll come back to that in a while. But I want to also discuss some of the other work that he had in the paper, which was actually a very fascinating, very nice article. So he also studied highly recursive graphs, and this is actually, he also proved that this is actually different from a decidable graph. So he studied the intermediate notion between computable and decidable of a highly recursive graph, whereby a graph is highly recursive if it is computable and the degree of each vertex is also computable. What this allows you to do is that if you have a vertex, you can generate immediately all of its neighbors And so you never have to guess if new vertices are going to be connected to the vertex that you're looking at. And what it then showed was that he showed that in every separating pi01 class, you can actually encode the paths into a highly recursive graph, which is k-colorable, in a way where the paths in your in the pi01 class corresponds exactly degree-wise to the k-coloring of the graph. So this theorem here kind of almost establishes a relationship, right, between WKL and certain graph coloring principles. So he needed to use separating classes because his aim was to have a one-to-one correspondence between the degrees of P and the coloring of G, rather than just encoding it into G. But this is going to be kind of related to what that we're going to be talking about next. Okay. Another interesting thing which he showed also was that he also showed that every highly recursive planar graph has a computable 6 coloring. So if you further assume that the planar graph is highly recursive, then you can actually, with 6 colors, you can actually produce a computable coloring of the graph. And the proof roughly goes like the following: because the graph is highly recursive, you could generate layers of, right? You can start with a node, and it can generate all of its neighbors, and then you can generate all of the neighbors, and you can think of the graph as building up layer by layer. And because the graph is highly recursive, you actually will not have any intersection between the different layers. And every time a new layer come out, you kind of with some clever trick, you can kind of color it with three colors each time. So 3 plus 3 equals 6. That's why you can get 6 here. And as far as I know, perhaps someone can if someone who knows can tell me if this is true or not. But as far as I know, this question which was raised in that paper is still open, whether every highly recursive planar graph has a computable 4 or 5 coloring. This I think is not known. Nevertheless, Schmel generalized his results by saying that by showing, in fact, that every highly recursive k-colorable graph has a computable 2k-1 coloring, and this result is sharp. And there is a related result by Kerstedt, who shows that if you further assume that the highly recursive graph is also perfect. A perfect graph is one where the chromatic number of every subgraph is equal to the size of the largest clique. So that means that every finite subgraph can be colored using the minimum number of colors that are necessary. If you have a graph that's like this, then you only need k+1 many colors to get a computable coloring. Okay, so I'm gonna just quickly talk about some related questions about edge coloring. So Kerstedt also showed that every highly recursive, so basically the theorem from before was about vertex coloring, and basically he also showed that this was true for edge coloring. There is a well-known theorem by Weising which goes along the lines of the following. Every k-regular graph is a graph where the vertex is of every degree is exactly k. Actually, his theorem was about less than or equal to k-regular, but I'm just gonna use k-regular here. Every k-regular graph has a k+1 edge coloring. And if you combine the two theorems here, that actually tells us that every k-regular computable graph, of course, has a computable k+2 edge coloring. And yeah,
Selwyn, I think there's a question in the chat.
Oh, no, Stefan, no. The graph that doesn't have to be connected. No. Yeah. Okay. So yeah, okay. So combining these two theorems, that actually tells us that every k-regular graph has a computable k+2 edge coloring, whereas Schmel shows that you cannot replace k+2 by k. So there is a computable 3 regular graph that has no computable 3 edge coloring, which leaves the fascinating question of whether you can have a computable k plus 1 edge coloring. So namely is Bayesian theorem computably true. And again, also as far as I know, this computable version of Bayesian theorem is not known for edge coloring, which is if anyone knows more, I'm happy to discuss. It's quite a fascinating question. It's not very easy to it's harder than you might think. And also I want to mention a related work of Carl, who actually shows that WKL is equivalent to what is known as Koenig's line coloring theorem or Koenig's edge coloring theorem, whereby it has a similar flavor to kind of the statements that we've been discussing. If you assume that you have a bipartite graph, then you can always have a k edge coloring where k is a bound on the degree of the graph. Yeah, so in other words, if you have a bipartite graph, you can get the coloring to be k. Okay, so that's kind of the work that has kind of motivated the stuff that I want to talk about. So so as I mentioned, I really want to be discussing the four-color theorem. So the first issue, right, you have to kind of think about is how are you going to formalize planar graph, because there's kind of a few definitions that's classically equivalent. So I'm going to so again, all graphs are simple, and I'm not going to assume any other properties apart from being planar. So they do not have to be locally finite, or they do not have to be connected unless we say so. And instead of always saying over RCA naught, I'm going to just assume that. And this is the definition I'm going to take. So a graph is planar if and only if K33 and K5 does not embed as a minor or as a subdivision of K. So the famous so for finite graphs, this is actually equivalent to having a plane embedding. The first as a minor is by Wagner, and the subdivision is well known, is Kuratowski's theorem. For finite graphs, right, this is actually equivalent. But if we want to have an infinite graph, how we're going to represent a plane embedding. So I'm not going to call the plane embedding an embedding, because I'm not going to require the map, the embedding itself, to be computable, but merely that the range as a diagram is computable. So I'm just going to call it a plane diagram of an infinite planar graph. Is going to be an infinite set of rational coordinates that makes up the coordinates of the vertices on Q squared. And for edges, I'm going to allow finite each edge in the embedding. I'm going to allow to be composed of finitely many connecting line segments, and this is mostly for convenience, right? So that when you're building a diagram, you can kind of curve your way around obstacles if you have to. There is a related there are related works by for example, by Wagner, Ferris, and Stein. For finite graphs, actually this is actually equivalent to having a plane embedding whereby you have straight lines as the edges, and Thomason generalized this to infinite graphs. The reason I'm not going to be talking about straight lines is that it's much harder to construct embeddings using straight lines, because you have to kind of predict in advance things that might appear and will get in the way. So I'm just going to allow curves, the edges to curve around stuff. But what I do want to mention is that it is also interesting to study like the exact content of these theorems, as far as I know, is also not known. Yeah. So how this all comes together is a theorem really observed by Erdős. Of course, he didn't quite state it in this way, but essentially what he observed was that using the usual compactness argument, you can show that every countable planar graph has a plane diagram, has a plane diagram, right? And the reason this is true is because if you're thinking of constructing a plane diagram in stages, if you have a finite plane diagram of a finite subgraph, then there are only finitely many faces that this thing generates. So the next vertex that comes along can be put into finitely many different faces, of the faces, and that allows you to construct the finitely branching tree that encodes the plane diagram as a path. But the question is, well, we kind of need a WKL to do this. The question is this computably true? So the first thing maybe I want to discuss is that just as a warm up, to construct, it's not actually that hard to show that there is a computable graph that has no computable diagram. And if you kind of think about it, you can actually because we're not gonna I'm not gonna assume that the embedding or the isomorphism to the diagram is computable, but merely that the diagram itself as a set of vertices is computable. So what we're gonna have to do is to kind of build the graph to be just using the usual tricks in when you're building computable structures, to kind of make each gadget or component distinguishable from each other, maybe using cycles of a fixed length or something like that that doesn't interfere with planarity. So if you're watching like the ETH computable diagram, partial computable diagram, for example, then we want to kind of introduce a gadget of these 1, 2, 3, 4, of these 6 vertices, and then in the computable diagram that we are trying to diagonalize, there are actually only these 4 possible ways that he could put down this particular gadget, right? Whether V4 and V5, the 2 vertices here, whether they are both on the same side of the face generated by the 4 cycle here, right? So on the top left, you have V4 and V5 both on the exterior face. On the bottom right, you have V4 and V5 both on the interior face, and then the other 2 are representing 1 on each side. But of course, since the diagram is computable, you kind of watch which one shows up, and then you do the usual thing where you just kind of make it impossible for him to extend the diagram. So for example, if he gives us the top left configuration, then what we do is that we add the 6th vertex on the inside and connect V6 to the 4 vertices here, as well as connect to V5. Now remember, all we need to do is to build a computable graph. So we could of course rearrange this to make it planar, but in the computable diagram he can't really rearrange because he's already put down these 5 vertices, and actually you see that there is no way that he can connect V6 because he cannot put V6 on the inside because that doesn't give him access to V5, but he cannot put it on the outside because that doesn't give him access to either V1 or V3, whichever way he puts. So yeah, so that's going to make it impossible for him to extend the diagram. So in fact, we can do a little better. Not only can you make it not completely true, but you can in fact encode all every tree into this statement. So you can show that WKL is equivalent to the statement that every planar graph emits or has a plane diagram. And that actually tells us that if we're working over WKL, then we can kind of interchangeably we don't really need to be very careful about the various definitions of what it means for planar, for a graph to be planar. So these are the principles that we looked at. So as usual, we parameterize K with K, where K is the number of colors, and the main principle I'm going to look at is COLK, which is the K color theorem of planar graphs. You could have variations such as COL star, where you require the graph to be presented in the form of a diagram. So every graph with the computable diagram is K colorable, and you can also look at the connected version of the K color theorem. So every connected planar graph is K colorable. Yeah, so there are some differences between them, but for the most purpose of this talk, I'm just going to be looking at the first principle here. Okay, recall the theorem of Bean before, and that actually immediately tells us that that the K color theorem is not computably true for any K, no matter what how many colors you can use. And it's not hard to show that the four-color theorem is in fact equivalent to Wick's and X lemma. And yeah, so just a quick just a quick diagram here to kind of illustrate this. First of all, from WKL to the four-color theorem is just the usual compactness argument. You do have to check that the classical proof of the four-color theorem doesn't use more induction than sigma 1, but that's not really a problem. So the main task is to do the reversal. So you want to reverse the four-color theorem to WKL, and what you do is you assume that you have a tree and you want to kind of encode the tree into a planar graph. And so what you do is you introduce a gadget, for example. So the gadgets are basically identical. You have this basic gadget here, and you attach the same gadget to the two nodes N0 and N1. And obviously, this gadget here is meant to stand for the root node of the tree. And this one here is meant to stand for the 0 extension, and that for the 1 extension. And you can kind of stick the similar stuff on at the ends. And what you then do is you say, okay, if neither of the two extensions of sigma dies, then you don't do anything to the gadget that encodes the node sigma. But if, for example, the 0 extension dies, then you kind of extend them using 3 new nodes, whereby you put 2 here on the left that connects to 0, that marks the fact that 0 has died, and you put just 1 and you connect to the existing edges in this way. And it's easy to see that any four-color theorem of the whole graph has to color this gadget. But because if you look at these 4 vertices, this is actually a 4-click 1, 2, 3, and 4 here. So they have to use all 4 colors here. But now you look at these 4 nodes, 1, 2, 3, and 4. That's also a 4-click, which forces him to use the color 1 here, and then that allows you to say that this also must have color 2. But on this side, you can make the same argument to say that this has to have the missing color 2 and 1 and 2. And so therefore, what this says is that any 4 color of the whole graph must have the property that this black vertex and this black vertex is the same, and this vertex and this black vertex are different. So by looking at the color of the original set of nodes, you can kind of deduce or predict which of the extensions survive on the tree. And we're going to be doing similar encodings subsequently. Okay. Now, of course, if you notice, this graph that we built is also connected, and we never mess with the diagram. So that actually reverses not only the four-color theorem, but the other versions that I've also mentioned. Yeah. So what about the k-color theorem for k larger than 4? So in the reversal that I just described here, we actually used the 4-click as an integral part in the proof in the reversal to kind of force any 4-color to have very little choices, and that's very important. So we obviously cannot use K5 in a similar way to reverse the 5-color theorem because the graph has to be planar. And using K4 wouldn't do the trick because 5 is bigger than 4, and that's gonna allow him to that's not gonna allow us to extract very much information from a 5-color of a graph if we are using a graph that's similar to the one before. So we're gonna have to try to use a different trick. And as it turns out, to reverse the k-color theorem for k larger than 4, it has to be done non-uniformly, and for k at least 7. This is provably necessary that you cannot reverse uniformly. So instead of trying to reverse to DNR2 or WKL, we want to reverse to DNRK, and just to recall, the DNRK is a principle that there is a that there is a function with range from 0 to k minus 1, one of k many possibilities, where G is different from the universal partial computable function. So to encode, to reverse the 5-color theorem, we are going to reverse the DNR3. So let's just quickly see how this is done. So what are we doing here? So we want to build a graph with the property that any 5-color theorem of the graph, any 5-coloring of the graph computes a DNR3 function. So we are obviously we're going to have to encode the universal function into the graph. And the way we do this is the following. So we start with the 3-click or the triangle, and we start with six of them, 3 on each side. So we put 3 on the left and 3 on the right, and we have a total of 3 times 6, 18 vertices. And if phi e doesn't converge, then we don't do anything. But if phi e does converge, then there are 3 possible cases. Either it converges to 0, 1, or 2. And in each case, we want to leave a different kind of trace. So for example, if it converges to 0, we add 6 new vertices, shown here by the white in white. And what we do is we connect each of the 6 vertices to each of the 3 clicks. So like this one here gets connected to these 3 vertices. This one here gets connected to these 3. This one here gets connected to these 3, and so on. And then we also connect the 3 new vertices together to form a new 3-click on each side. Now I know this is not very planar looking, but it can be adjusted to make the edges not crossing. And if it converges to 1, then we just add 2 new vertices. The one on the left gets connected to everything on the first group, and the one on the right gets connected to everything on the second group, and then we connect the 2 new vertices to each other. That's if the output is 1, and if the output is 2, then we just introduce only 1 and connect to everything. And it's easy to see that if we are given the 5-coloring of the graph, then we can kind of deduce what is not possible, right? So for example, if we are given the 5-coloring of the graph, and the left set of 9 vertices here are only colored with 3 colors, right? So if these 9 vertices are colored with only 3 colors, then we can conclude that this case is not possible, because if we only have 3 colors, then this 3-click must use up all 3 colors, and same here, and that leaves only 2 colors for the remaining white vertices, and of course you can't do that. So this case is not possible if the given 5-color colors this with only 3 colors. The second case is if the left and the right set of vertices are colored with 4 colors, but the same set of 4 colors, then we know that the second case is not possible, because that leaves only the 5th color for this and the 5th color for that, and that's not possible. And finally, if all 5 colors are used, then the last case is not possible. So depending on the characteristic of the 5-color, we can kind of guess, or we can kind of know which of the 3 cases are not possible. Yeah. So that's a typical encoding of the DNR3 into the graph. Okay. Now, so what that tells us is that the 4-color theorem and the 5-color theorem can both be can now both be reversed, but there are some slight differences, right? So in the first reversal, we did it uniformly for to DNR2, but in the second reversal, we didn't. We had to have the help of DNR3. So so the natural question to ask is why, and how can we is there anything we can say more? So as per usual, if you want to calibrate the complexity of statements which are equivalent but have different proofs, we use the tools of computable analysis. So this is suggested by this group of authors who use the Weyrach similar ideas and suggested this definition in the for statements of second order arithmetic. I think most people are familiar with these definitions. Now, the only thing I want to point out is that the difference between the strong and the non-strong version is just that when you are given the solution, in the strong case, you don't need to know the original problem in order to get a solution to the original problem. But for most of the principles that I look at, in fact, the two are equivalent. So I'm not going to really distinguish between them. And the idea is that if the principle P is reducible to Q, then usually, provided that induction isn't a problem, one can usually turn it into a proof of Q implies P. This is what we had. So as per discussed, the 4-color theorem uniformly reduces to a DNR2. The 5-color theorem uniformly reduces DNR3, and the 6-color theorem reduces 4. But when you get to 7, something strange happens. You don't get 5, but you actually need you need to have 8 possible values in the range of the DNR function. So one would, of course, think that this goes on, right? So if you have the 8-color theorem, then you should have you should be able to fill in with DNR something for a suitably large value here. But as it turns out, that the 8-color theorem does not actually reduce to DNR. So in the interest of time, of course, I'm not gonna really discuss this, but the basic idea is that why it all fails spectacularly when we get to 8 colors is due to the very simple fact that 8 is 4 plus 4, and the 4-color theorem is true classically. So that allows you to kind of do some kind of an extension whereby you fix a 4-color theorem, where you apply the 4-color theorem to color the original finite subgraph, and then for the rest of the graph, you can just use a different set of 4 colors. So that's why for 8 color, you cannot use the same trick as from before. So what can we do then if we want to reverse the 8-color theorem? Well, as it turns out, the simple solution is just to add more layers of non-uniformity, and the trick is to define is to consider non-uniform versions of DNR. So I have the definition here in case anyone wants to look at it. But essentially, what this principle here says is that K is still the same as before. K is the number of values that the DNR function is allowed to have. But L is basically the number of mind changes that you're allowing your DNR function to have. So instead of having the DNR function being computable, you have the DNR function being allowed L many different values. And you also will have to allow the universal function to have a number of different possibilities. But if you adjust the parameters in the right way, you can have the correct principle DNR K, L. And by using 2 different parameters, we can show that the n-color theorem, in fact, reduces to DNR Kn, Ln for parameters which are dependent on n. Yeah, and also this thing is equivalent to WKL, and that allows the reversal. Yeah, so in the last part, I'm just gonna focus on the hierarchy between these different principles. So if we have the n coloring theorem, the n coloring theorem with computable diagrams, and the n coloring theorem for connected graphs. So kind of the reversals that we had to the proof of the reversals that we had to go through for the n color theorem for different n kind of suggests that depending on the value of the parameter, you would need different levels of different kinds of non-uniformity. And so it would be interesting to see how these principles compare, at least from the point of view of the Dirac degrees. Right. So we've seen that the 8-color theorem does not reduce to WKL, but the 4-color theorem does. So what about the values between 4 and 8? It turns out that the 7-color theorem does not also reduce WKL, and this proof is a little bit it has to be a little bit different. So because the NR8 actually does reduce to the 7-color theorem, so we cannot just use the same proof as we had for the 8-color theorem. It's not going to be quite as simple as that, but with some work you can get that the 7-color theorem does not reduce to WKL. Right. So what we then explored was to compare these levels in general, and so here's an example of something that you could show. Every 4 levels of the k-color theorem is proper. So namely that 4n plus 1, 4n plus 2, and 4n plus 3 color theorem does not reduce to the 4n plus 4 theorem. And again, it's because every time you have 4 more colors, you can kind of use the same trick as before. You can just use the 4. You can use the different set of 4 colors to color the rest of the graph. And you can also have similar extensions for the connected coloring theorem and the star version of the coloring theorem, except that for the connected version, because when the graph is connected, that kind of restricts the kind of coloring that you have. So we can have 3 here instead of 4. And for the star version, you will need slightly to adjust the parameters here slightly. But anyway, what we do get out of all of this is that the k-color theorem as a principle is not below either the connected coloring at the same level or the star version of the coloring theorem at the same level. So it's kind of interesting that depending on the properties of the graph that you have, you cannot get them computably equivalent. Okay, so I'm going to just finish with a few remaining questions, and these are all of a slightly technical kind. So one interesting question is whether there is a uniform reduction to WKL of the 5-color or the 6-color theorem, right? So we know that the 7-color theorem is not possible and the 4-color theorem is possible, but we don't know for 5 and 6 whether you could reverse uniformly. And just generally, what happens in between every 4 levels, we don't know like the relationship between 4 adjacent or consecutive parameter values. But we do know that every 4 levels that you have non-collapsing. Yeah, and the exact relationships between the different versions. So for example, if you look at the k-color theorem, what is the smallest value of n that allows the k-color theorem to reduce to it? So we know that if n is as small as 4, then it's possible. But if n is k itself, then it's not possible. But it would be kind of interesting to see how the number of colors will affect the uniformity of these reductions. Some of the other things that we also wanted to study, but we didn't have time to do so, was that it would also be interesting to study in the same context the other kind of surrounding principles that arises from having other restrictions on the graph. So for example, what if you assume that the planar graph was locally finite, or if you assume that the planar graph is highly recursive? these I believe would generate different principles. And one should also look at the strength of the Ferris theorem, which is remember the theorem that says that every infinite planar graph has an embedding with straight edges. So this I do not know if it can be done in, for example, in Witt-Koenig's lemma, or what is known as Groch's theorem, which is that every planar graph that is triangle free has can be colored with 3 colors. So that would also be something interesting to look at. And finally, we didn't really look at the comparing with other principles that arises in the entire zoo of wire degrees and closure under these other operations. So that would also be nice to clarify. So I think that's it. Thank you for your attention.
Thanks, Ellen, for the colorful talk. Any questions? Hold on.
Thanks. So one kind of principle that sort of would be, well, basically pointwise SWKL, but is sort of not in a uniform way, is for example, given an infinite tree, give me 2 things, at least one of which is a path through it, or 3 things, and so on. Yeah, basically the more candidate things you can try, the easier that thing is. Have you tried comparing those to the coloring, or do you have any intuition whether these look like promising candidates?
No, yeah, I think you bring up a good point, because some of these principles, for example, the 4-color theorem, right? That there's no problem with doing it with identifying it with paths on the tree. But once you increase the parameters, I think that something breaks down. So I think yeah, I think this would be a good direction. I'm not really sure what it would bring though. Yeah.
Other questions? Oh.
So call K, is it trivially closed under parallelization? Like just take a bunch of graphs and just squeeze them together in the same plane and.
Yes, I think yes. I think it. Well, yeah. So when you parallelize, I guess you have things that are disjoint, right? So yeah. So I think that would be that would be yeah. Yeah. So perhaps this is not a good. I don't know. I just wrote down the first thing that I thought of, but perhaps it's not a good example. But yeah. But there are other things that there are other things that I think would make sense.
Okay, and another question. I understand that all these principles are with the definition of planar, which is given by not having those minors, right? So if you change the definition to the other one that you showed it's equivalent under WKL not, but in weaker theory it's not equivalent, you will get weaker principle, I understand, right? Do you have any results about those? I mean, just
no.
Let's say the 4-color theorem for graphs which have actually a planar diagram. Yeah.
So there are different. Okay, so one can even go down to the level of so even for minor and subdivision, that they're actually slightly different, and I think one of them is stronger than the other. But for planar graphs, they're actually equivalent. So these 2 definitions I think we can take to be equivalent. But no, you're right. So for the definition for this one, you definitely need for this one you definitely need WKL. Yeah, so I guess if you if you work in a weaker system, then yeah, then you would have a different principle. I'm not sure. It would be difficult to work in a weaker system because just generally it would be difficult to work in a different system, in a weaker system, because you would not even have a way to even color the whole graph. So yeah, I don't know.
Okay. Any more questions?
Sorry, just on that. I guess it would be difficult to work. So in all of this, we kind of build the plane diagram. So this is actually the principle that we prefer to use. I guess it would be really difficult to use the other definition as a principle on its own. I'm not sure if. I guess you would have to develop new techniques for that.
Keita, go ahead.
So if we just consider non-uniform version mean and just computable reduction, then does everything just collapse to one of WKL or just trivial, or there can be still intermediate thing?
No, there will still be intermediate, because you can still do the diagonalization.
Okay.
Yeah, you will still be able to do the diagonalization.
But
that doesn't.
Can we say that is strictly weaker than WKL or some cases?
Yeah, for 7, for example, it would be strictly weaker. This one.
Okay. Oh, I see. Okay. Mm-hmm.
Yeah.
Okay. Yeah. Thank you.
Other
we don't
questions?
know. So sorry, we don't know for 6 and 5. I think if anyone wants to try that, that's really. I mean, I tried pretty hard, but it seems yeah, it seems pretty tricky.
Okay. Thank you.
Other questions online or in person? Okay, well, let's thank Thelwyn again for the colorful talk. And Selwyn, we're going to have lunch.